Hey guys, Zong here, back with another math video. For the past few weeks we've been doing USIMO problems, but Daniel wanted to do his last one, and I feel as if some of our viewers are very accustomed with USIMO problems because they're a bit harder than AIME problems. So just for this week we're going to go back to AIME problems. This is a problem from AIME 2008, number 8 I think, from AIME 2, not sure. And just try to solve it. And pause the video if you need to. Okay, so the first interesting thing about this this sequence, I should say, is the existence of two cosine A sine A. And this little expression has a interesting property in that since we always want to split up the cosine from the sine because that gets really annoying really fast. This is actually equal to sine A plus B minus sine A minus B. And why is that? Well, sine A plus B is equal to sine A cosine B plus sine A sine cosine A. How could I screw that up? Cosine A is zoned out. Sine B minus sine A cosine B minus cosine A sine B. And if you just reduce this, these two cancel out, and you're left with 2 cosine A sine A. And now that we know that this is true, we can actually this expression is originally summation of from k equals 1 to n of, let's see, 2 cosine k squared A sine k A, if k goes from 1 to n in this sequence, which it does. So since we now know this expression, we can actually convert this into summation of k equals 1 to n of sine k plus 1 A minus sine k minus 1 k A. And why is that? Well, the reasoning for this is that if we substitute this in for this, I probably shouldn't have used A in my example, but they did that on the AOPS website, so I just did it too. If we sub in k squared equals A, oh yeah, I made a typo here, whoops, and k for B, then of course A plus B is just k squared plus k, and A minus B is just k squared minus k, and these simplify to k times k plus 1 and k minus 1 times k. So that's why this works. Since this is just sine A plus B and sine A minus B, that's what it is. Sorry for the repeating variables for A, that's gotta be confusing, but that's basically what these are, and that's why this expression works out. So let's just try writing out the first few terms of this. So if we have k equals 1, the first term is sine 1 times 2a, so sine 2a. Second term is sine 0 times 1a, so sine 0, plus sine, now we move on to k equals 2. 2 times 3 is 6, and 2 times 1 is 2, 6a, minus sine 2a. And for k equals 3, 3 times 4 is 12, sine 12a minus sine 6a. And as you can see, this is a telescoping series because at every term, each term cancels out. So sine 2a cancels out with this sine 2a, sine 6a cancels out with this sine 6a, and it just keeps going down the line until you get to sine n plus 1a made a mistake, it should be a minus sign, minus sine n minus 1a. So dot dot dot, you get there. Now all the terms cancel out except sine 0, and so this cancels out with something later, and then blah blah blah. This term doesn't cancel out either, because remember, a term only cancels out if it's met with a, so sine 2a cancels out with negative sine 2a, which comes after it. But since the series stops here, nothing comes after this. Nothing comes after this series. So that means that there's nothing to cancel out this sine n plus 1a, because there's no other terms after it. But this thing cancels out with something from here that comes before it. So this shows up, sine n minus 1a, so it shows up here, and it cancels out. So these two terms are the only thing that's left, which means that this summation really just simplifies to sine n plus 1a minus sine 0. And sine 0 is just 0, so we can ignore that. Now let's see what we want. So we want this to be an integer. So sine n plus 1. Remember that a is pi over 2008. I wonder why they used the number 2008. It will always remain a mystery. But yeah, just making sure. So is a integer. Okay, well, what values of sines are integers? Well, that means this has to be from -1, 0, or 1. And sine will give -1, 0, or 1 if when given sine x, so given an expression within x is a multiple of pi over 2. So whenever x is a multiple of pi over 2, and you're going to just draw the unit circle here. Here's pi, sine x is 0. Here's pi over 2, sine x is 1. Here's pi, that's 0, and here's 3 pi over 2, and that's just a -1. So whenever pi's the expression is a multiple of x over 2, that's that's going to be an integer. So that means n plus 1 pi over 2008 is some integer. We'll call this integer k. I like k pi over 2. So given k is an integer. So pi's cancel out, which means that, and we move 2 to that side. So n plus 1 over 1004 equals some integer. Now we got to find the smallest n for which this works. This should be pretty simple. One factor of 1004 is one factor, prime factor. The largest prime factor of 2004 is 1004. 1004 is 251. I think this is prime, but it is definitely a factor. And so the top has to have somewhere in here 251 as a factor of the numerator. So why don't we just try n equals 2051. And n plus 1 is 2052. N plus 1 is 2052. 2052 is divisible by 4. It has a factor of 4, and 4 times 2051 is indeed 1004. So excuse me. So if you multiply these two together, you do indeed get a multiple of 1004, and thus it's a when you divide them, it gives an integer k. And it turns out this is actually the smallest. You can check some other numbers. So n equals 251 is the solution. I'll see you next week.